I am Jin Wu from Technical University of Munich. Today I'm going to present our work, Structured Learning for Cyclic Linear Causal Models. This is a collaborative work created by our mathematical statistics group with Federica Onori, who is from Sapienza University of Roma. A linear causal model consists of a random vector x which solves the equation x equals lambda transpose x plus the error epsilon with covariance matrix omega. Omega does not need to be diagonal. Then x is inverse of the transpose of I minus lambda times epsilon and has covariance matrix by the formula below. We are specifically interested in models restricting support of lambda and omega, that is, given by a mixed graph. Linear Gaussian model given by mixed graph corresponds to the set of covariance matrices of this form in which lambda has the support the directed edge set and omega has the support the bidirected edge set. Here is an example of linear causal model. The equations relating four variables are shown on top left, and this can be easily represented by the mixed graph on the top right, where the directed edge weights are marked in blue, the red ones are bidirected edge weights and node variance. The edge omega 14 means there exists a latent variable having influence on both x1 and x4. In this example, the graph is simple. That means there is at most one edge between any pair of nodes. We will focus on this kind of simple graph in our paper. These are our main theorems. The expected dimension theorem says the linear Gaussian model given by a simple mixed graph has dimension equaling parameter counts. The sufficient condition theorems. Two graphs with same skeleton and collided triples are distributionally equivalent up to closure. That is, mg1 equal to mg2 up to a measure zero set. This theorem generalizes not at all layer sufficient condition for simple acyclic mixed graphs. We can also say that the expected dimension theorem provides a necessary condition for distributional equivalence, namely having the same number of edges. To perform model selection, we propose a score based on log likelihood and penalty, BIC type penalty. We consider standard BIC and extended BIC. The latter has an extra term and tends to find sparser graphs. Since the model space is extremely huge, we use greedy search. It starts at some initial random graph generated by MCMC. At each step, it traverses the local neighborhood of the current graph by adding, removing, or changing one edge. Finally, the search stops when no higher score in local neighborhood or the maximum number of iterations is reached. To address the issue of local optima, we restart the greedy search hundreds of times. This table shows the result for 5 variables, 100 simulations, and 300 restarts for each. By our theorems, the proportion of same dimension gives an upper bound for getting distributionally equivalent models as the true graph, and the proportion of same skeleton and collided triples is a lower bound. We choose different sample sizes with 10,000 samples. The true proportion of getting distributionally equivalent models range from around 0.4 to around 0.7. The structural Hamming distance is the number of adding, reversing, or changing needed from one graph to another. The SHD star is the minimum of all SHD between the graphs that can be certified equivalent by our theorems. This distance is around 2. That means, in average, our estimated graph needs 2 operations to reach the true equivalent class. We also apply our method to a protein expression data. From Sachs et al., the 14 datasets of 11 proteins are obtained under different experimental conditions. Cycles are expected because of the self-regulation of those proteins. We adopt Gaussian coupler model, which assumes every variable is a transformation from some latent Gaussian distribution. We use Kendall's tau correlation matrix as the covariance input and choose extended BIC because the graph has 11 nodes. Below, these are 2 estimated graphs. The second graph presents a 3-cycle. Our estimations show agreements with Sachs et al.'s paper and find some novelties as well. For more information, we invite you to read our paper. That's it. Thank you.